All right, for 4.5 in Algebra 2, we are doing inverse matrices and solving systems. Okay, our objectives today are to determine whether two matrices are multiplicative inverses, determine whether a matrix has a multiplicative inverse, find the inverse of a matrix, and to solve a system of equations using an inverse matrices. So lots of stuff here with inverses. So first of all, I want you to recall. Okay, so think about that 1 over a and a are multiplicative inverses. Remember, that means if we multiply them together, so 1 over a times a, the a's would cancel and it would leave us with 1. So if we had like 1/4 times 4, that equals 1. 1/10 times 10, that would equal 1, right? Because the 10s would cancel. That's the multiplicative inverse. Okay, so we're multiplying by the inverse, or the reciprocal, you might say too. However, all right, so a multiplicative inverse matrix, okay, of matrix A, that's n by n, doesn't matter if it's a 2 by 2, a 3 by 3, whatever, is denoted as A to the power of -1. Okay, so it's an n by n matrix as well, such that if we take matrix A times the inverse matrix, it's the same thing as if we take the inverse matrix times the original matrix A, and either way it's going to equal 1. Okay, it equals 1 no matter, sorry, it equals I, the inverse matrix. Pardon me, not 1. It looked like a 1 up here. So it equals I, that inverse matrix. Okay, so this is commonly referred to as the inverse matrix. Here, it's good to know that the commutative property of multiplication holds true for multiplicative inverses. And we kind of see that here, right? It doesn't matter if we do A times its inverse or the inverse times A. The commutative property applies. Okay, so in example 1, we want to determine, I'm going to clear some of this. We want to determine whether matrix A, 4, -2, 5, -3, and matrix B, 3 over 2, -1, 5 over 2, and -2 are multiplicative inverses of each other. The way to do that is we need to find AB, so A times B, and B times A, to see if they are multiplicative inverses of each other. Okay, so let's start with AB. Okay, so we're going to take and do our multiplication. Remember, because this is a 2 by 2, we're doing a 2 by 2. This one is a 2 by 2 as well. So we're multiplying a 2 by 2 times a 2 by 2. So the two numbers on the inside are the same, so we can multiply, and our solution is going to be a 2 by 2. All right, so this is going to be, I'm just going to do the math here. So 4 times 3/2 plus -2 times 5/2 is that first spot. Then we're going to move over and multiply by the second column. So we're going to have 4 times -1 plus -2 times -2. Let's change colors and go to our second row. So we're going to have 5 times 3/2 plus -3 times 5/2. And then we're going to keep that second row, multiply by the second column. So 5 times -1 plus -3 times -2. Okay, so if we're looking here, 4 times 3/2, right, the 4 would cancel and become a 2. 2 times 3, this is 6, plus the 2 would cancel, so we would have -5. 6 plus -5 is 1. So I have 1. 4 times -1 is -4, plus -2 times -2 is a +4. -4 plus 4 is 0. So I have -1, or I have 1 and then 0 in this spot. Unfortunately, I've taken up my room here on this one. Okay, so here, nothing cancels, so I'm going to have 15 halves plus, and here nothing cancels, so negative 3 times 5 is negative 15 halves. So that equals a 0 in that position. 5 times negative 1 is negative 5, plus negative 3 times negative 2 is a positive 6, so that gives me a positive 1 in that position. And if you recall, that is an inverse matrix, because the inverse matrix has a 1 in every spot on the main diagonal. Everything else is a 0. Okay, so now let's solve for BA. Okay, so I'll draw my line there. Let's do BA. Okay, so for BA, we're going to start with this one. So I'm going to have 3 halves times 4 plus 5 halves times negative 2 in this spot. And then, right, 3 halves. Hold on. I did that wrong, right? 3 halves times 4, negative 1. It's my first row. Yeah, so there should be negative 1 times 5. All right, see, it helps me to rewrite them, but that's okay. So 3 halves times 4, and then I'm going to take this, because I'm taking this row times this column. Maybe I'll just circle them. So I'm going to have negative 1 times 5. Okay, now I'm keeping my row, and I'm multiplying by this second column here. So I'm going to have 3 halves times negative 2 plus negative 1 times negative 3. Okay, now, I'm ready to move to my second row, 5 halves, and my first column. Okay, so I'm going to have 5 halves times 4 plus negative 2. So 5 halves times 4, and so negative 2 times 5. And then I'm ready to move to my second column. So 5 halves times negative 2, right, plus negative 2 times negative 3. And I'll close it up. Okay. Oh, that just took a minute to get figured out. So here, 3/4 times 2, the 2 cancels, the 4 cancels, becomes 2. 3 times 2 is 6, plus negative 1 times 5 is negative 5. That gives us a positive 1. Here, 3 halves times negative 2, that cancels, gives us a negative 3, plus negative 1 times negative 3 is a positive 3, so that's a 0. Here, we don't have anything. Let's see, the cancels. Yes, we do. The 2 cancels, the 4 cancels, becomes 2. 5 times 2 is 10, plus negative 10, so that's a 0. Here, our 2's cancel, so we get negative 5 plus negative 2 times negative 3 is a positive 6, so that's a 1. And again, we have 1's in the main diagonal. Everything else is a 0. So, yes, okay. These are, let's see, so we'd say yes, A and B are multiplicative inverses. Are multiplicative inverses. Okay, because both A times B and B times A equal the identity, right? So we could say inverses because A times B equals B times A equals the identity matrix. So they are multiplicative inverses of each other. All right, so I'm going to have to erase all this so we can look at the next part of it. Okay, so it says if matrix A equals ABCD and the determinant, remember this is determinant symbolism, so if the determinant of A is not equal to 0 then the inverse of A is equal to 1 over the determinant of A. That's kind of nice, right? Instead of doing all the work, we can find the determinant of A and write 1 over that, and we're going to get the inverse. Okay, so what that also means, or it's the 1 over the determinant of A times, we'd have D, negative B, negative C, A. So it's a little handy there. If the determinant of A equals 0, however, the multiplicative inverse is undefined. Okay, so let's give example 2 a try. We're going to find the inverse of each matrix. Okay, and so we're going to use this information up here to help us. So first we need to find the determinant of A. Okay, so remember, the determinant of A equals, we're going to do the main diagonal, so 1 times negative 4 is negative 4. And then we're going to subtract the minor diagonal. So negative 2 times 5 is negative 10. So negative 4 minus negative 10, which is the same thing as plus a positive 10, gives us a 6. Okay, then it says the inverse of the matrix. So the inverse matrix is going to equal 1 over the determinant of A. We found the determinant of A to be 6. So this is going to be 1/6 times, okay, and we're going to multiply it by switching the elements in the diagonals, right, into this order. So we're going to put D here. So in this case, let me erase these. Okay, D, this was A, B, C, D. So we're going to put D in the first position. So it's going to be negative 4. Then we want a negative B. So B is 5. We're going to make this negative 5. Negative C. So C was negative 2. So now it's going to be positive 2. And A goes in this position. A was 1. Okay, so we have 1/6 times negative 4 times negative 5 times 2 times 1. All right, remember to multiply, right? We have a scalar multiplication here. We're just doing multiplication. That 1/6 is getting distributed to every element. So 1/6 times negative 4 is negative 4/6. All right, we'll reduce them afterwards. I just want to see them. 1/6 times negative 5 is going to be negative 5/6. 1/6 times 2 is 2/6. 1/6 times 1 is 1/6. All right, so let's simplify this. So we're going to have negative 4/6 is equivalent to negative 2/3. Negative 5/6 is just going to stay. Doesn't simplify. 2/6 is equal to 1/3. And 1/6 is also already simplified, so it stays. Okay, so that is your inverse right there. Okay, that's the inverse matrix, A to the negative 1 power. Okay, let's do B. So let's find the determinant of B first here. So we're going to have negative 3 times negative 4 is a positive 12 minus 6 times 2 is 12. So 12 minus 12 is 0. Wait, what did it say about 0? If the determinant of A, or in this case B, equals 0, the multiplicative inverse is undefined. So we would say B to the negative 1 power does not exist. Or you could say it's undefined. However there. Okay. So it's nice if you get to this point, you're like, bam, I am done. I don't have to go any further. That is the nice thing about the determinants. They don't always seem like a shortcut, but they are if it equals 0. Like you can determine that part faster than solving multiple steps. Okay, next up. Solving matrix equations is similar to solving linear equations. Okay, so to solve the matrix equation ax equals c for x, okay, we're going to left multiply each side of the equation by the inverse of matrix A. Okay, so if you think about this, it's the same, like I said, it's the same thing as if we multiply a linear equation. Okay, if we have 4x equals 8, we can divide by 4, or we can multiply by the inverse or the reciprocal, right? Because 1/4 times 4 cancels and leaves us with x. 8 times 4 is 2. Okay, so a lot of times we divide, but we can use the multiplicative inverse. We use this most often when we have fractions. Like if we had 3/2 x equals 12. Okay, in this case, the multiplicative inverse is 2/3. Okay, so the 2's would cancel, the 3's would cancel, we would still be left with x. And then 12 and 3 would cancel, right? This would be 4. 4 times 2 would be 8. So it is the same thing as if we solved a linear equation, but a lot of times we don't use the multiplicative inverse or the reciprocal unless it's a fraction. And that's what it's showing here. Okay, so if we have ax equals c, we can multiply by the inverse on both sides. So then we're going to get the inverse times the inverse of a times the matrix A is going to cancel. And we're going to get 1x equals the inverse of matrix A times c. And so that's our final answer when we simplify. X equals the inverse of A times c. Okay, now that I've tried to give you some background on why this works, let's see if we can actually put it into action to solve example 3. Okay, so in example 3, we are solving the matrix 6, 8, 2, 3 times x equals the matrix -2 times 0. All right, so we want to find our inverse so we can multiply by our inverse, okay, in order to do this. So to find our inverse, remember we need to take this matrix, we need to find the determinant of A. So 6 times 3 is 18, minus 2 times 8 is 16. That equals 2. Okay, that's our determinant of A. Before that, recall that we said the inverse of A, matrix A, is equal to 1 over the determinant of A times matrix, well, times the D, negative B, negative C, A. Okay, so that's what we're using here. So to do this step, we found the determinant of A is 2. So our inverse of A is going to be 1/2 times D. Again, I'm going to erase here so I can get a clear vision of my numbers. So D goes here, so that was 3. Negative B, so we had a positive 8, it's going to be a negative 8. Again, feel free to label these. This is A, B, C, D. We want negative C. It was positive 2, so now it's going to be negative 2. And then we want A, so 6. Okay, so let's simplify and get our inverse matrix. So 1/2 times 3 is 3/2. 1/2 times negative 8 is negative 4. 1/2 times negative 2 is negative 1. And 1/2 times 6 is 3. Okay, so this is our inverse matrix right here that we need. Now that we have our inverse matrix, we can solve the equation. Okay, so we're going to take our equation here, 6, 8, 2, 3 times x equals matrix -2, 0. Okay, we're going to multiply by our inverse matrix on both sides. So we're going to multiply by 3 over 2. Put this matrix here. -4, -1, and 3. Now, the nice thing about this is that we know this is the inverse matrix, right? This is the inverse matrix of A, and this is matrix A. So when we multiply the inverse matrix times the original matrix, so A times the inverse of A, we get an inverse matrix, which is 1, 0, 0, 1, X. Okay, so we don't even have to do that math. Like, we know that this is going to equal the inverse. Okay, where we do have to do it is on the other side, because we're multiplying both sides by the inverse matrix. So 3 over 2, -4, -1, 3. All right, so this is where we got to do the math. Now, let's check here real fast. We're multiplying a 2 by 1. Oh, time out. Multiplication matters. Order matters. I can't, the way I've written this, I just caught myself. This is a 2 by 1, right? It's 2 rows by 1 column times a 2 by 2. I can't multiply it in this order. I just caught it. I have to put this one first in order to do it. So let me go back here. Dun, 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 dun. See, this is when order matters in matrices. Okay, so I need to put my inverse matrix first. 3 over 2, -4, -1, 3. Okay, I'm going to multiply that by my C. Oh, I tried to change colors and I missed. So multiply that by my C, the -2, 0. Okay, so now let me go back and check. I'm glad I did that. So I have a 2 by 2 matrix that I'm multiplying by a 2 by 1. So yes, I can multiply now because my 2's are internal, and my solution is going to be a 2 by 1 matrix. Okay, so notice that, like, you multiply each side of the equation by your inverse, but your inverse needs to come first. Okay, so this equals, all right, so now we're back to matrix multiplication. So it's this row times this column. Okay, and it's going to be a 2 by 1. So it's going to have 2 rows, 1 column. So I'm going to do 3 over 2 times -2 plus -4 times 0. That's a 0, not a 6. All right, then we're moving down to the second row. So -1 times -2 plus 3 times 0. All right. So the 2's cancel here, and let me change my color so I could track it a little easier. My 2's cancel, so I have 3 plus -4 times 0 is 0. So this is a 3. Oh, that was a -2, wasn't it? So it's -3. My bad. When I crossed it out, I couldn't quite see it. So that's -3. -1 times -2 is a +2, plus 3 times 0 is 0. So this is a 2 here. All right, so X, because again, this is the identity matrix, so we can actually just get rid of it and say, all right, X equals -3, 2. And there we go. We have solved for X. We've solved for our unknown matrix here. Okay. Whew. We are making good progress. You're probably like, I don't know, Miss Talbert, it's 24 minutes, but we are. All right, the last one, we're going to look at a word problem and apply this. So example 4, the sum of twice a number and a second number is 8, while 3 times the first number plus twice the second number is 13. Find the number by writing a system of equations and solving the related matrix equation. Woohoo! Let's do this. So we're going to write a system of equations and solve the related matrix equation. So first of all, we've got to write the system. Okay, so the sum of twice a number and a second number is 8. This is the first one. Sum is addition. So the sum of twice a number. So we're going to have 2x plus y means equals 8. Okay, now we have to use the same variables, right? Or it's not going to make sense. While our next one says 3 times the first number. Okay, so that's going to be 3x plus, so that's plus, twice the second number, so that's going to be 2y, means equals 13. Sweet! Okay, so there is our system of equations. So we need to transfer this to a matrix equation to make it make sense. So our matrix equation is going to be 2, 1, 3, 2. We're pulling out those coefficients. All right. We have an x and a y in here. And for our constant, or our C matrix, we have 8 and 13. Remember, because this is that A, x equals C matrix equation. All right. So in order to solve this, I feel like I might have skipped a part. No, I didn't. I'm just checking to make sure that I'm good. All right. So we're going to take the steps that we used on the previous one, right? We wrote this equation. Do you remember how we solved it the last time? Okay, we have to find the inverse of A. What is the inverse of A? All right, so we need to find the determinant of A first of all. Okay, so 2 times 2 is 4. 3 times 1 is 3. So 4 minus 3 equals 1. Okay, to find the inverse of A, it equals 1 over the determinant of A times negative d b. Let's see. Nope, that's not right. I was trying to do it from memory, and I'm failing. It is d negative b, right? Yes. So it is d negative b. They either switch places or they're negative. Negative c a. Right? A and D change places. B and C just become negative. That's how I generally remember it. Okay. All right. So this is equal to, let's plug stuff in now. The determinant of A is 1, right? We found that here. So this is going to be 1 over 1 times, which isn't going to change anything, right? Okay. Up here, here's our A, our B, our C, and our D values. So D is 2. Negative B, B was 1, so it's going to be negative 1. Negative C, C was a positive 3, so it's going to be a negative 3. And A was 2, so we're going to put a positive 2 right there. Okay, so our inverse of A, let me just rewrite it here. The inverse of matrix A equals, I'm getting smaller and smaller, 2, negative 1, negative 3, 2. That is our inverse of A. Okay, so how do we use this inverse of A to solve this equation, AX equals C? Do you remember? Okay, we're going to multiply it on both sides. Okay? All right. So sorry, I had to go talk with a child. Somebody else is in the building and they startled them. Okay, so my question was, how do I use this inverse to solve this? If you recall, hopefully you've had time to do that, we're going to multiply both sides by the inverse. And that's going to leave me with just this piece, right? Because the here is just going to cancel when we multiply it. It's just going to leave me with this. So I'm going to pick up there, okay? What I'm going to do is I'm just going to write, all right, this is x, y is going to equal our inverse matrix, so 2, -1, and -3, 2, times our constant matrix, 8/13. Okay, so this is so now I've got my X matrix equals my inverse of A matrix times my constant matrix. Okay, if I was looking at it like that. Again, if we check, I have a 2 by 2 matrix. I'm multiplying by a 2 by 1 matrix. So yes, I can multiply because my two numbers in the middle match, and my solution is going to be a 2 by 1, which it should always be a 2 by 1, right? I should have a value that's equal to x and one value that's equal to y in my matrix. All right, so let's do the math. Okay, so I'm going to have 2 times 8 plus -1 times 13. And then move into my next column. So -3 times 8 plus 2 times 13. All right, again, I'm going to change color so I can kind of track it. 2 times 8 is 16. -1 times 13 is -13. What's 16 plus 13 equal? Or 16 plus -13, pardon me. Good, is a +3. Okay, then -3 times 8 is -24. Plus 2 times 13 is a +26. -24 plus 26 is a +2. So my x matrix, so x, y, equals 3, 2. Which means here that x equals 3, right? Y equals 2. If I had to write this as a solution, my solution would be 3, 2. Okay. But again, so my x value here is 3, my y value here is 2. All right, that is it, okay, for today's lesson. I can't wait to see you guys tomorrow and go through some questions. Have a great one. Bye.